Guys, welcome to my channel, The Mechanical Engineer. So here we have a question based on mechanical vibrations. We have to find the natural frequency of vibration of the system shown over here. So in this question we have two springs with stiffness K1 and K2. We have a rod pivoted at point O at one end, and we have a mass M at the other end. The springs K1 and K2 are joined to a fixed support at one end and to points A and B, which are two different points on this rod. So we have to find the natural frequency of this system. So here this is the displaced position of this pendulum M. So when this rod displaces in this direction, so this spring with stiffness K1 elongates, that it has tension in it, and the spring with stiffness K2 compresses. So the rate of elongation of tension in the spring K1 is the deflection is x1 into theta, and the deflection in spring 2 is x2 into theta. So here we see the free body diagram. So here we have a force K2. When this spring K2 is compressed, it will try again to come to its original position. So there will be a force from here on this rod. See this force, which is F2, that is K2 into X2, and the spring K1, which is in tension, will try to compress itself a little to come to its original position. So this rod will have a force in this direction due to this spring K1, which is K1 into X, and this inertia force I0 theta double dot. Now from this figure we have the deflection in spring 1. It is not in both spring, it is only in spring 1, that is x1, which is equal to A into theta. The A is the distance of the spring from here. This distance is the distance A, and the spring force or restoring force due to spring 1, that is F1, which is equal to the stiffness of the spring into the deflection, which is A theta. So we put the value of A theta over here. We have K1 into A into theta. Similarly, for the compression of spring 2, we have x2, which is equal to B into theta, and the restoring force is equal to K2 into x2. We substitute the value of B theta in x2, and the mass moment of inertia is the mass into the length and its square. So here we don't have L2, we have M into L square instead of this 2 over here. So now we are only going to solve it from the equilibrium method. So in equilibrium method we have the sum of inertia torque plus external torque is equal to 0. So the inertia torque is I theta double dot, and the external torque we have in two springs, that is K1 x1, which is F1, and F2 is equal to K2 x2. So then after this we will have, in external torques we have F1 plus F2, which is again equal to K1 x1 plus K2 x2, and we have to multiply distance over here. The distance for K1 x1 is A, and for K2 x2 is the distance B, the distance at which it is deflected. So here we have I theta double dot, which is written same from here, and the K1 A theta into A. We have substituted the value of A theta in the place of x1 over here. So we have K1 A theta and the distance A over here. Similarly for K2 B theta into the distance B, and mg sine theta into L, the force acting from the pendulum over here in the displaced position will be mg sine theta. So here we multiply the mg sine theta and the distance of this rod, which is L, from the pivot O. So here we have I0 theta double dot we take the theta common from both of these equation. From all of these three equation, we have k1a2 plus k2b2 plus mg into L. Since the angle theta for sine theta is very small, so we consider it as theta. So here we have theta, we don't have sine in the next step, which is common. So this is the next equation. Now after solving this equation, we get theta double dot plus k1a2 plus k2b2 plus mgl upon I0 into theta is equal to 0. What we do in this equation is we take this whole equation over here. So in this step we have I0 theta double dot is equal to whole this equation. Then we take theta double dot also on that side. So here we have multiplication, so when it goes that side it will be in the denominator, and then we again bring the whole equation from this side over here. So then we have this equation. So after we compare this to the differential equation of motion, we have the value for omega n square, which is equal to this value in the bracket over here. We have k1 a square plus k2 b square plus mg into L upon I0, which is inertia. So for omega n square we have this value, and then for omega n we will have a square root over here because we have to remove this square sign over here. So we have omega n is equal to root of k1 a square plus k2 b square plus mg L upon m into L square. We have substituted the value for I0 from here, which is ml square. So the natural frequency of vibration, which is fn, and its formula is omega n by 2 pi. So here we write 1 by 2 pi into omega n, and the value for omega n we write it from here. So the natural frequency, the final answer for the diagram, we have 1 by 2 pi root of k1 a square plus k2 b square plus mg into L upon ml square.